If this is a diagram of the Earth, and we have these kind of mysterious, kind of imaginary field lines drawn around it, they point toward the Earth, meaning that if we put something in those field lines, something is exposed to those field lines, like a little red ball, and then that little red ball is going to fall toward the Earth. It's going to move in the direction of the field line. The field line is kind of like the line that follows the curvature of space-time. This ball will follow the direction of that field line and fall toward the Earth. It experiences a force. The force experienced between that ball and the Earth is equal to g m1 m2 over r squared. m1 being either the mass of the Earth or the ball, m2 being the other mass. Okay, there is a force of gravity whenever you have two objects with mass. Let's take away that ball, though. If we take away that ball, then the force of gravity disappears. There is no force, there is no push or pull if there's nothing to be pushed or pulled. But if the Earth is what's causing gravity, it's what dents the fabric of space-time, then gravity isn't disappearing, it's just the effect of gravity has disappeared. So we use this concept of fields to describe the idea that gravity itself is still there. You can see the field lines surrounding the Earth. You can see that there's the potential to influence something, the potential to cause an effect on something, if I just put something there. Now I put the little green ball there. Hey, look, gravity hasn't mysteriously reappeared. The gravitational force has reappeared because the field that was already there, that was always there, is just now causing an effect on the object with mass, the little green ball. All right, so let's get rid of that little green ball again. This equation describes the force if there is a red ball or a green ball there, but we have to also describe the field, the influence of gravity or the potential influence of gravity, even when there's nothing there to experience it, that field. That gravitational field given by the symbol little g. Two equations that describe that, gm over r squared, and then of course we have g is equal to f over m. This is what we call the producer equation. This is what we call the experiencer equation. So when you have information about the Earth, then we're going to use the producer equation. Or whatever it is that's causing the field, you're going to use the producer equation. If you have information about what experiences the field, which you don't right now, right? There's nothing there to experience it. We would use the experiencer equation right here. If I was to put the little red ball or the little green ball back in that field, then all of a sudden we'd have both a producer and an experiencer. Write down your givens for both the producer and the experiencer and see which one you know more about. If you know more about the Earth, use this. If you know more about the green ball or the red ball, then let's use this. All right? A couple more little things before we check over our homework here. What does M stand for here? That should be, at least on the surface, a pretty easy answer. What does M stand for? I keep seeing a couple hands do this, but not really going up here. Yeah, Kirsten. It's mass. Mass of what, though? This would be the mass of the producer, the mass of the Earth in this case, right? If the sun was the producer, then it would be the mass of the sun. If you were the producer, then it would be the mass of you. Okay, it's going to be the mass of the producer. And this would also be M, but this would be the mass of the experiencer. This would be the mass of the little red ball or the little green ball, as the case may be. What happens if you have information about both? What happens, let's get rid of the green ball because it gets a little bit confusing when you got one producer and two experiencers. We got one producer now, the Earth, one experiencer, that's the little red ball. What happens if you have lots of information about both? You know the mass of the Earth. You know how far away from the center of the Earth the ball is. You know the mass of the ball. You know the force experienced by the ball or the weight of the ball. What happens if you know everything you need to know about both of these objects, the producer and the experiencer? Which one are you going to use? It doesn't matter. Okay, the field produced by the Earth is the field that's experienced by the little red ball. So if you have information about both, use whichever one you want. My suggestion, if you have information about both, would be probably to use this one, only because the math is a little bit easier in this one than it is in this one, right? You don't have to worry about the squared, and there's only two variables instead of three, and so on. All right, we had 3 questions on 218 for homework. Any issues with any of those 3 questions, please? Number 2? 1. Got 1, 2, and 3. 1, 2, and 3. What a coincidence. All right, number 1 says a satellite orbits Earth at a distance of 3 times our Earth above the Earth's surface. Our Earth is the radius of the Earth. So the satellite is up here, and the distance from the surface of the Earth to the satellite is 3 times the radius of the Earth. Okay, we know what the radius of the Earth is. It's on our data sheet. I think it was 6.38 or 6.37 times 10 to the 6. We know that the surface of the Earth is 1 times the radius of the Earth away from the center. So that answers question A right now. How many Earth's radii is the satellite from the Earth's center? It's 4. 4 times the radius of the Earth from the Earth's center. Now, what's the magnitude of the gravitational acceleration of the satellite? What's another way to ask that question? What's the magnitude of the gravitational acceleration? What's another term that means the same thing as gravitational acceleration? We've just been talking about it, right? Terry? The gravitational field. Now we have 2 equations that describe gravitational field. There is the producer equation and there's the experiencer equation. The Earth is the producer. The satellite is the experiencer. What do you know more about? Doesn't look like you know much about either one of them here. But if you look at your data sheet, you know more about you know more about the Earth or the satellite when you look in your data sheet? The Earth. So let's use the producer equation since we know more about the Earth. G is equal to big G, m over r squared. 6.67 times 10 to the minus 11. The mass of the Earth is on our data sheet. I think it was 5.97, is that right? Times 10 to the 24. And the radius of the Earth, I think, was 6.38 times 10 to the 6. Which we've got to square. We do the math there. Don't forget to square that. You do the math there, it should work out to be 6.11 times 10 to the minus 1. What units could we use? I just cheated and looked at the answer there to see what that was so I wouldn't have to calculate it. They had meters per second squared. Okay, can you use meters per second squared? Sure you can. Could you use something different? What other set of units could I use for gravitational acceleration or gravitational field? Nathan, number 2. Newtons per kilogram. 6.11 times 10 to the minus 1 newtons per kilogram. Listen, 4 times the radius of the Earth, that's a long way from the surface of the Earth. We would expect gravity to be small at that point above the surface of the Earth. Gravity never is 0. Gravity never completely disappears, right? We think of there being no gravity in space. There is gravity in space. It's just really, really small because the distance away from the producers, the things that cause gravity, is really, really big. Here, we're getting to have a pretty big distance. This satellite is really far away from the surface of the Earth. And because of that, gravity is really, really small. It's not 0. Okay, gravity is not 0. It's 10 to the minus 1 meters per second squared, as opposed to gravity on Earth, which is 10 to the positive 1. Okay, it's 100 times stronger on Earth than it is at this point. 100-ish times stronger. But it's not 0. There's still gravity there, just really, really small. If we go back to our field diagram for a second, we said on the very first day that the density of the field lines represents the strength. In other words, the further you are away from the producer, the further away the field lines are from each other, the weaker the field strength is going to be. When we're way, 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 way out here, then the field strength is going to be pretty weak, as we just found. All right, number 2. An 80-kilogram astronaut is in orbit this far from the Earth's center. Use the data on table 4.1, page 218, to find the magnitude of the field strength at the location of the astronaut and the field strength if the astronaut was orbiting the moon with the moon with the same separation distance. So here's the Earth. The astronaut is orbiting at 3.20 times 10 to the, I'm going to say 10 to the 7 meters. See what I've done there? See what I've done there? It's 10 to the 4 kilometers. I don't want kilometers, do I? I want meters. So I'm just going to convert that down. How do I do that? Multiply it by 1,000, or 10 to the 3. So 10 to the 4 becomes 10 to the 7 meters. Here's the astronaut up here. He's all happy because he's orbiting around in space there. His mass is 80 kilograms. So we want to find the field strength at that point. Now, what's the producer here, the Earth or the astronaut? What's causing the field? Who's causing the field here, the Earth or the astronaut? Yeah. The Earth. So therefore, the astronaut would be experiencing the field, right? The field at that point that's caused by the Earth is the same as the field at that point that's experienced by the astronaut. Is there a mistake?
Yeah.
What did I do? Oh, it does. Yeah, it's from the Earth's center. You're right. Okay, that's good, actually. That makes it a little bit easier for us. Because if it was like this, from the Earth's surface, what would we have to do? We'd have to add the radius of the Earth into it, right, to plug it into the equation. So this gives us a bit of a break. That's good. Thank you, Terry. The field strength caused by the Earth, Sam, is the same as the field strength experienced by this astronaut. What do we know more about? The astronaut or the Earth? It almost seems here like we know more about the astronaut, right? We know his mass or her mass. We don't know the mass of the Earth. Oh, but we do. If we check our data sheet, we do. So we know the mass of both. What else do we have? Well, we know the distance from the Earth. That goes with the producer. Do we know the force experienced? We do not. So we know more about the producer. Hey, listen, worst case scenario is you try the experiencer equation. What happens? You're missing two givens. You're missing two variables. You don't know this, which is okay because that's what you're trying to find, but you also don't know this. So you can't do it. It's okay to try it. You just can't do it. Try another equation. Try the producer equation. The mass of the Earth, be careful to use the mass of the Earth, not the 80 kilograms. 5.97 times 10 to the 24. And R is 3.20 times 10 to the 7. And don't forget to square that. When we do the math there, it should work out to be 3.89 times 10 to the minus 1. I'm going to say newtons per kilogram, but could have been meters per second squared, just like we did in the last one. I'm not going to do B, but we'll tell you how you would do B. What would be the magnitude of the field strength if the astronaut is orbiting the moon with the same separation distance? What would change? Okay, what would change if you're talking about the moon? G wouldn't change. The separation distance isn't changing. The only thing that changes here is the mass, right? So you plug in the mass of the moon as opposed to the mass of the Earth. That's on your data sheet as well. When you get that, I'm not sure what the value is here, and I'm not going to cheat and look yet. I will, but not yet. Would you expect to have a bigger number or a smaller number? Same distance, smaller mass. Bigger number for G or smaller number for G? Sorry? Smaller number. We'd expect that number to be about 1/6 of what it is for Earth. So let's scroll down here. Sure enough, we get 4.79 times 10 to the negative 3 newtons per coulomb. Newtons per kilogram, I should say. What did I say, newtons per coulomb? Newtons per coulomb is not gravitational field. That's electric field, and you'll learn about that next year. Newtons per kilogram is what we need here right now. Is that okay? Who asked me for number 2? Is that good? Okay, finally, number 3. Man, the highest satellites orbit Earth. A satellite is something that orbits around something else, and that's our next topic, actually, that we'll take a look at on Tuesday. We'll do it on Tuesday. We'll finish it on Tuesday. We'll spend a little bit of time for review on Wednesday before our test. A satellite is something that orbits around something else. Okay, satellites orbit the Earth all the time. There's dozens or even hundreds of them orbiting around the Earth. Communication satellites, spy satellites. The International Space Station is a satellite because it orbits around the Earth. Even though we don't think of it as a satellite, Okay, it's a workstation, it's a laboratory, but it's still a satellite because it orbits around the Earth. The highest ones orbit around the Earth at incredibly big distances, 6.6 times the radius of the Earth from the center. We want to know the force on a 70-kilogram astronaut at this location. So let's draw the picture. Here's the Earth. The Earth has a radius RE to the center. Sorry, we don't need that, do we? Because just like in that last question that Terry pointed out, the distance that we're given here is to the center of the Earth. Pay attention to that, right? If it says it's 5.6 times the radius to the Earth's surface, then you need to add the Earth's radius to it. If you're given the distance to the Earth's center already, then you don't need to add anything to it. You're good to go. What if you're given the field or the force and you're asked to solve for the radius, the distance to the surface of the Earth? If you're asked to solve for the distance to the center, solve for r. If you're asked to solve for the distance to the surface, solve for r and then subtract the radius of the Earth, right? All right, what's the force on a 70-kilogram astronaut at this location? There's two options here. Okay, here's the first option, and I think this is the easiest. Solve for force. The mass of the satellite is, or the astronaut, I should say, is 70. The mass of the Earth is 5.97 times 10 to the 24. And the distance here is 6.6 times 6.38 times 10 to the 6. Square it. Done deal. Okay, whatever that works out to be, 16 newtons. That's a pretty small value, right? 16 newtons. This 70-kilogram astronaut on Earth would be about 700 newtons. Here, he or she is only 16 newtons. Astronauts don't go that high, by the way. Okay, astronauts don't hang out at 6.6 times the radius of the Earth. No, it doesn't say whether he's alive or dead. No, it doesn't. Astronauts have gone that far. Astronauts have gone to the moon, right? And the moon is further away than that. But astronauts don't hang out at satellites orbiting around the Earth at that distance. The astronauts generally, when they're orbiting Earth, orbit on the same level as the International Space Station, which is, take a guess, how far away do you think that is? How far up do you think that is? 2.8 times the radius of the Earth? It's actually surprisingly close. It's less than 400 kilometers from the surface of the Earth. Okay, we're going to drive to Edmonton on the 29th in 2 weeks, 2 weeks from today. We will drive as far to Edmonton as the International Space Station is from us as it orbits overhead. It's just easier to get to Edmonton than it is to the International Space Station, that's all. It's no further. It's just easier. It's no closer. It's just easier to get there, that's all. Okay, we're talking 400 kilometers above the surface. This is ridiculously huge compared to that, right? All right, what's the other way of doing it? Well, some of you may have found the field strength caused by the Earth. Once you found the field strength caused by the Earth, you could use that and say, well, it's going to be the field strength experienced by the astronaut. So let's turn around and take this number that we just found for the Earth, put it into the field strength experienced by the astronaut, and then solve for the force experienced by the astronaut. What do you think you get? It's no coincidence that you get 16 newtons there. All right.